So you can see it and you can hear me, yeah?
Yep.
Okay, perfect. So first of all, I would like to thank the two organizers, so Sergey Filipov and Vitaly Turiansky, for the invitation and for providing me the opportunity to present the work of my group here. And I would also like to congratulate them for organizing this this very nice conference. And today I will be talking about poly-2-isopropenyl 2-oxazoline, and to show you what we can do with this polymer. Before starting, I would like to show you where we are located. So we are located in the heart of Bucharest, which is the capital of Romania, and is a very city, and it has also very interesting architecture, and in some way is similar to Paris. As you can see, we also have a Triumph Arch and other monuments. And if you ever have the chance to visit Romania, then just feel free to do it. So before starting the actual presentation, just a few words about what we do in my group. So the research activities in my group concern the development of functional molecules and new synthetic strategies that enable access to dynamic and complex molecular systems. So what we try to do, we try to use engineering, and we aim to develop new process for the development of smart material. We also don't discriminate between the chemistries that we use. So we use organic chemistry, we use polymer chemistry, chemical physics, supramolecular chemistry, in order to achieve our goal. We try to integrate functions into our materials, and for this we use this bottom-up synthetic approach, and from the molecular level up to the macromolecular scale. And what we do, we design functional compounds, as you can see here, functional building blocks that they have a functional group and a reactive group. And this reactive group allows us to further transform this building blocks into the final materials that we want to synthesize. Basically, we design and synthesize new organic materials with applications in photonics. We develop special azodyes for materials that show nonlinear optical properties, for obtaining photosynthesis, and for molecular engineering of the second and third order nonlinear properties. We also try to integrate various dynamic function in complex materials, and for this we develop multifunctional organic materials with complex response to external stimuli such as pH, temperature, enzyme, and so on. And finally, the last topic in the group, it's related to development of organic three-dimensional materials. And by three-dimensional materials, I mean hydrogels, micro, and nanoparticles, and fibers and nanofibers recently. So, and to develop this materials that I show you, we based our research on 2-oxazoline, and these 2-oxazolines are very well known in chemistry, especially for their reactions with different nucleophiles such as carboxylic acid, amines, thiols, and so on. But they are also well known in the polymer chemistry, where I think most of you know about the leading cationic ring opening polymerization of this heterocycle, which gives access to polyoxazolines that are now being seen as a very good substitute for PEG. However, we are not doing this cationic ring opening polymerization, but what we are trying to do is to preserve this oxazoline ring as a pendant group in the polymer. So we are synthesizing monomers that have a polymerizable group here, namely 2-isopropenyl 2-oxazoline, and then we polymerize these monomers and synthesize the polymers that retain this functional in the side chain. So although polyoxazolines synthesized by crop are more well known than this polymer, they do not yet reach commercialization But the polymers possessing this oxazoline units as pendant groups, they are already available on the market for, I think, more than 10 years. And they are sold by Nippon Shokubai, a company in Japan, but this company has also doing this in Europe and in the USA, and these polymers are sold under the trademark of Epocross, and they are used as reactive copolymers for coatings, for inks, and so on and so forth. So we started our work, I think, 15 years ago in the field. So back then we are very interested in obtaining copolymers of ipox, of this monomer with styrene and methyl methacrylate, and we did this by free radical polymerization. However, we are not very happy with the control over the distribution and over the molecular way, and then we turn our attention to anionic polymerization, and we optimize the conditions for the synthesis of this polymer by anionic polymerization, and now we are able to synthesize the polymers with molecular weight between 5 and 35 kilodaltons with narrow dispersity and very high conversions. And now why we are so interested in working with this polymer is because it has several interesting characteristics, and these characteristics are related to its water solubility in organic solvents from such as chloroform, THF, dimethylformamide, acetonitrile, and so on and so forth. So chemically inert to oxygen and to some extent to water. It has non-cytotoxic character. We can obtain it with well-defined characteristic, mainly by anionic polymerization, but also recently by ATRP or ZLRP. And what it's very important, you can perform post-polymerization modification reaction on it with carboxylic acids. And this reaction, this post-polymerization modification reaction with carboxylic acid, it's very interesting because it has a series of advantages over other post-polymerization modification reactions. First of all, the reaction conditions are very simple. So you just have to mix the polymer and the carboxylic acid in a certain ratio and then heat it. You have a quantitative modification degree under suitable conditions. The reaction doesn't require any catalyst and no byproducts are formed. You can easily isolate your product by precipitation or by freeze drying. And what it's very important, you can perform one-pot modification reaction using multiple carboxylic acids. As you can see upon the ring opening of the oxazoline ring, you have the deformation of an ester amide structure, which you will see it further in the presentation, how we try to use this structure to synthesize degradable materials and other type of materials. So what we have been able now to obtain until now, it's fluorescent azopolymer-based sensors, azopolymers for optical data storage, thermoresponsive polymers for biomedical field, multi-responsive polymers for detection and sensing, and a very recent drug conjugate for cancer therapy. But we'll only be talking about a few of them. So in our earlier work, what we tried to synthesize were some microparticles, and for this we used dispersion, non-aqueous dispersion polymerization, and we used methyl methacrylate as a comonomer, and by using this technique, we are able to synthesize these microparticles that had at their surface the oxazoline units, and these oxazoline units were further modified with a specially constructed azo dye that shows photoresponsive properties, as well as being used as fluorescent sensors. We use the same strategy, so this time a copolymerization in solution of this monomer with either methyl methacrylate and styrene, and we synthesize these copolymers that we further modify them once again with an azo dye, but this time this azo dye was specially designed to show nonlinear optical properties. And what we are able to obtain after synthesizing these copolymers is very thin films. And we were able to, by using second harmonic generation microscopy, to write the image, in this case of Georges Méliès, in this very thin polymer films with a very good resolution, and we are able also to read it afterwards. So this polymer, they show a very high potential of being used in optical data storage as data storage media. Of course, as I already mentioned, this polymer, it's water soluble, so it's very hydrophilic. So in theory, if we would modify it with some hydrophobic units, then it should show some LCST transitions. And this is what we did. So we took acetic acid, propionic acid, butyric acid, and isobutyric acid, and we modified the pipox, and we are able to obtain polymers that show cloud point temperature in between 10 and 90 Celsius degrees. We also obtain some quantitative correlation between the degree of modification and the cloud point temperature. And as you can see, we can nicely tune the cloud point temperature either by increasing the amount of the acid of the propionic or butyric or isobutyric acid, or by changing the hydrophobicity of the acid. Of course, for some applications, it may be undesired to still have unreacted oxazolene units onto your polymer backbone. So that's why we try to modify it completely. This time the polymer, and for this we used acetic acid, which is the hydrophilic unit, and another co-acid, propionic butyric or isobutyric acid, as hydrophobic unit. And as you can see in this case, also we are able to obtain a very nice correlation between the cloud point and the co-acid content, and we could nicely modulate the cloud point temperature depending on the hydrophobicity of the co-acid and the amount of the co-acid that was, and the ratio between the two acids used to modify the pipox polymer. Because oxazolines are known to react with the various nucleophiles, and they are known to be quite water unstable, the monomers, then we also perform some stability and we tested the degradation of this polymer under several conditions. And what we observe is that it's quite stable in water and at basic pH, especially at pH 9, while at acidic pH, as expected, it can be hydrolyzed. However, what I have to mention is that upon hydrolysis, there is no generation of any toxic product. So, for example, the polymer changes its structure to this hydroxy metacrylamides polymer, which is known to be biocompatible as well. Nevertheless, the polymer is quite stable for some time, mostly for a week in all the simulated media that we have tested. So up to now, you have seen application that involve the modification of pipox with monocarboxylic acids, but we can also use dicarboxylic acid, and in this case, we would gain access to cross-link materials. And this is what we did. So we synthesized hydrogel material for drug delivery application, ultra-high mechanical strength hydrogels for water purification, molecularly imprinted polymers, and nanofibers. In our first attempt, we tried to cross-link pipox with different aliphatic dicarboxylic acid, and for this we chose a range of dicarboxylic acid, starting from succinic acid and ending with dodecandioic acid. And we can, as you can see here, we can nicely modulate the swelling, the equilibrium swelling degree, so the swelling of the hydrogel depends on the acid that we used, and also when the hydrophobicity of the cross-linker is increased, we can also gain access to hydrogels that show a volume phase transition temperature, which is broader than in the cases where you use directly a thermoresponsive polymer such as polyNIPAM or another thermoresponsive polymer. We tested these hydrogels for drug release of two very well-known drugs, namely 5-fluorouracil and sodium diclofenac. And as you can see, depending on the nature of the crosslinker used, we can nicely modulate in both cases the drug release of these two drugs. We also tested the cytotoxicity of these hydrogels, and they are shown to be non-cytotoxic, and also to show to be protein repellent, and they do not promote mineralization, which is quite important if you're aiming for ophthalmic applications such as lens. Because previously we used quite, let's say, harsh conditions. So we use a solvent, dimethylacetamide. We use the high temperature 140 for the synthesis of the hydrogels. We were quite unhappy. So we wanted to move a little bit closer to the bio application. And then we changed the solvent to water. We changed we lowered the temperature to 60, and we used different dicarboxylic acid because this time we wanted to create degradable hydrogels. And as you can see, we use malic, tartaric, and some amino such as cysteine or aspartic or glutamic acids. And what we are able to obtain is degradable hydrogels. And I will show you here just an example of the degradation that is taking place in PBS. So we tested the stability of these hydrogels in different media. But in here you have only the graph for PBS, and as you can see, for malic and tartaric acid, you have a continuous increase of the swelling degree of this hydrogels, which shows that this hydrogel degrade in PBS, while the other hydrogels they are quite stable. We tested this also by compression experiment, and as you can see, the compression strength after incubation in PBS drops dramatically for the malic and the tartaric acid, biphosphocinic acid, which was used in this case to show that there is no degradation. The compression strength remains similar after 2 weeks of incubation in PBS. We also performed some cytotoxicity studies, and we showed that degradation products of these hydrogels are non-cytotoxic. Using Pipox, we also synthesized hydrogels that were used as for the water purification, and we did this by using a crosslinker, namely a derivative of pillar 5 arene that can host inside different guest molecules, and as you can see here, depending on the amount of the crosslinker used, we can obtain different hydrogels, and in here you have the swelling behavior of these hydrogels, and as expected, once you increase the amount of the crosslinker, the swelling degree of the hydrogel decreases. However, upon complexation with paraquat, which is a known guest molecule, you can see that the swelling degree of this hydrogel increases, and also the color of the hydrogel is changing because the hydrogels were transparent, but upon complexation you can see that they show the characteristic red color. We tested also the compression properties of these hydrogels, and also you can see that upon complexation of the paraquat, you have an increase in the mechanical properties of these hydrogels due to the guest host interactions. Further on, the hydrogels for the pollutant removal of some well-known contaminants in water, such as methylene blue, methyl red, bisphenol A, and 2-naphthol. And as you can see, we have a very good efficiency for methyl red, methylene blue, and bisphenol A, and we can have this cycle, this regeneration cycles repeated over many times, and we do this by washing with EMF, which removes the dye, and then we have the trapped dye, and then we can reuse again the hydrogel. Using the same strategy with a bit of modification, we also synthesized the dual cross-linked hydrogel using terpyridine. So this time we took pipox and we modified it with a terpyridine carboxylic acid, and we obtained a pipox terpyridine polymer, and this polymer we cross-linked it with azelaic acid, and in this way we generated a chemically cross-linked hydrogel. Afterward, this chemical cross-linked hydrogel was soaked in metal ion solution, and we generated the dual physically and chemically cross-linked hydrogel. And for the complexation experiments, we used metals such as nickel, cobalt, copper, iron, and zinc that are well known to complex the terpyridine units. We tested the swelling properties. We performed also some rheology measurements, which are not shown here, and we also tested the compression of these hydrogels. And as you can see in this graph, we have a huge increase in the compressive modulus and in the toughness of this hydrogel upon complexation with zinc iron, which at first was unexpected for us because we expect this to happen for iron, but actually the zinc has the advantage that it forms thermodynamically stable complexes with the terpyridine. However, they are kinetically labile, and this allows the formation, the reformation and formation of the complexes throughout and the formation of a more efficient network compared to the iron when using the iron. In the last part, what I would like to show you, it's the work related to imprinted polymers. So we use this time as a cross-linker a dicarboxylic acid that has dithiol bond, and this dithiol bond is susceptible to cleavage with reducing agents such as glutathione or TSEP. In our case, we use TSEP, and in here you have the same images of the MIPS that we were able to obtain. We tested this MIPS with 5-fluorouracil, so we use as imprinting molecule the 5-fluorouracil, and we tested the drug release of the 5-fluorouracil, and as you can see at pH 7.4, you have an increase of the drug release upon adding TSEP, and also at pH 6.5 notice the same behavior of the molecularly imprinted polymer. This brings me to the end of my talk, and I hope I have shown you that this polymer can be useful in the synthesis of a wide variety of materials, from pH light responsive to hydrogel, molecular imprinted polymers, and to particles and fibers. I would like to thank to the members of my group for performing a part of this experiment, but also to Professor Richard Hohenboom, where also part of the work that was presented here was done in his lab while I was a postdoc there, and to thank you all for your attention.
Thank you.